Morning, everybody. Welcome back to Calc 2. Today, on our last non-exam day of class. Holy smokes. Plan for today is I have a quiz for you on Standard 15, and then we're going to jump into what would have been Standard 16, kind of something that we've been building up to with our discussion of power series, which is the discussion of a particular type of power series called a Taylor series. I'll have office hours on Monday at 11 and 1. I will be holding office hours next week in preparation for y'all's final exam next Friday. They might not be the usual office hours. I'll let you know on Monday when those office hours are going to be. But on Monday I will have my usual office hours. Don't forget y'all have an exam Monday. That's basically like a mini final over standards 1 through 15. Anything you still need, you can do on that. And don't forget you all have a web work due tonight. So, exam Monday. You all can go ahead and have 2 sheets of notes for this one, front and back, whatever you want written on them. Bring them into the exam. And also, I'm not 100% caught up on like retest grading and such over the last 2 days in particular. So I'll try and get those graded by tomorrow, and once I do, I'll update Canvas again and send everyone an email letting you know that, hey, Canvas is updated, here's where you stand mastery-wise going into Monday's exam. Any questions or comments before we get going? Y'all are a lively bunch, huh? Me smirks at that as usual. You all really are getting tired. Now, in fact, a math major was once given the following question on a physics exam. You are given an accurate barometer. How can you use it to determine the height of a skyscraper? Student answered on the exam. I would go to the top floor of the skyscraper, tie a long piece of string to the barometer, lower it until it touches the ground, and then measure the length of the string. The professor's not happy with that answer, so goes up to the student after exam and says, look, can you give me another method, one that demonstrates your knowledge of physics a little better, using a barometer? Hint, hint. Math student says, sure. Go to the top floor, drop the barometer, measure how long it takes to hit the ground, and find the height from that. No, that's not quite what I had in mind. Let's try again. Okay, says the student. Make a pendulum of the barometer, measure its period at the bottom, then measure its period at the top? No. Again, the professor demanded. Measure the length of the barometer, mount it vertically on the ground on a sunny day, measure its shadow, compare it to the shadow of the skyscraper? This is ludicrous, says the professor. Again! Walk up the stairs, use the barometer as a ruler to measure the height of all the walls in the stairwell? Last chance, young man. Find where the janitor lives, knock on his door and say, please, if I give you this barometer, will you tell me the height of the skyscraper? Well, the story is more than one way to answer questions sometimes, if you're clever about it. All right, and with that, let's go ahead and do today's quiz. You all know the drill by now? Have fun. go ahead and take a few seconds to finish up your thoughts. And pass your quizzes in, please. All right. How are y'all holding up? Yeah. As I say, I know it's a busy, stressful time. Classes are ending on what, Tuesday? Final exams are coming up. Want you to know y'all are great. You've got this. Just hang in there a little bit longer. Do your best. Okay, so I'm not going to test you over what we're going to talk about today. I'll just lead off with that. Doesn't mean it's not important, valuable information. It's just that we're not really going to have enough time for me to talk about it in enough detail to feel comfortable giving you assessment on it. But what we're going to be talking about today is basically, why do we care about power series in the first place? There's a lot of different areas in math in which the idea of power series show up. There's one kind of topic in math where power series are most common. And that's in actually trying to compute functions that are using computers that are not very nice. So, you likely saw in Calc 1 some sort of idea of how you might approximate something like square root of 4.1 using a tangent line. You're given a function of square root of x. You go to a nice point like that's close to 4, or that's close to 4.1, like x equals 4. Find a formula to the tangent line of this function. And then you could use that to approximate and say, square root of 4.1 is about equal to the value you would get using this tangent line. And in Calc 1, that's where we stopped, using the tangent line. Y'all are pros at this point, though. Calculus masters of the universe. That might be stretching. Y'all are calculus masters of a very small portion of math. So what we're going to be talking about today is not how do you use a tangent line to approximate a function, but instead what happens if you wanted to take a tangent parabola, or a tangent cubic function, or a tangent, dare I say, quartic or quintic function, or dare I say, a tangent polynomial of arbitrary length, or if I may be so bold, a tangent power series to a function. And that's going to be our goal for today, is given some non-polynomial, like the square root of x, which is a power function, but it's not a polynomial. instance, we might be looking at square root of x, e to the x, a trig function in terms of x, a lot of different functions that you could look at there. How can we find a power series that will converge to that function? It's Friday and class is in session. Sorry you had to hear that. Because here's the thing. If you ask a computer to find something like square root of 4.1 or e squared or sine of pi over 5, things that are not very nice numbers, computers are not very good at computing things like sines and square roots and exponential functions like e to the x. You know what computers are really good at doing? Polynomials and power series by extension. Dr. Gersel, how can a computer compute a power series? Isn't it like infinitely long? Well, you got me there. That's why a computer will never give you the full approximation for, say, something like what's pi equal to? They'll give you like 10 digits after the decimal and say, hey, it's close enough. But computers can compute expressions like e squared or square root of 4.1 or sine of pi over 5 from using power series expansions really, really quickly. And so that's what we're kind of going to be looking at today, is the topic of what would have been standard 16 and 17, and we have like another week to go in the class. How can you find given some function, how can you find a power series that converges to that function? Alright, there's 5 for you, 2, 3, 4, 5 for you, 6 for you, because I appreciate you so much. 1 for you. Nathan doesn't get as much appreciation. Alrighty, so what I kind of want to get through today is let's see if we can find a power series that'll converge to the square root function. Keep it fairly straightforward. And where I want to center that power series is at x equals 4. Just, kind of a nice number to plug into the square root function. I don't know how to take square root of something like 4.1, but I know square root of 4 should be equal to 2. So let's start off with our tangent line approximation to f of x equals square root of x, taken at x equals 4. All right. Those of you who had me last semester, I believe this was standard 14 last semester, maybe standard 13. It was somewhere around there. How did we find a formula for the tangent line to a function? Or maybe I should ask this first. How did we find the slope of the tangent line to a function? Rhoda?
Take the derivative.
Yeah. Slope of the tangent line, m, is just given by definition to be f prime of 4. Which, let's see, f of x is square root of x, which is x to the 1/2 power. F prime of 4 should then be 1/2 times 4 to the negative 1/2 power. If we do a little bit of power ruling, which is going to be 1/2 times 1 over square root of 4, which is 1/2 times 1/2, which is a 1/4. Okay, 1/4, neato burrito. Okay, we found the slope of our tangent line. How can we find a point on the tangent line? Something that'll allow us to use kind of our point slope formula for a line, perhaps. Well, think about it. Can anybody give me the x and y coordinates of some point that happens to lie on this line right here? Bethany?
4, 2.
Yeah, you just take 4, 2. Well, assuming I actually drew this out correctly, nicely. We can just take 4, 2 as a point on the line. Or in other words, we could take a, f of a. In this case, we're looking at a equals 4 to get the point 4, square root of 4, which is the point 4, 2. And so then our tangent line that we could take to our function, square root of x at 4, is going to have the formula y is equal to f of a plus f prime of a times x minus a. Which, when we plug in our values, our a value is 4, our f of a is going to be 2, our f prime of a is going to be 1/4, and so we end up with an equation for our tangent line of y equals 2 plus 1/4 times the quantity x minus 4. And if you wanted, you could simplify that further to get like 1/4 x minus 1 plus 2, so like y equals 1/4 x plus 1. I'm going to leave it like this for now, though. With the idea here of these are going to be the first 2 terms in a power series that we're going to be creating. And I'm going to give the tangent line a fancy name. Last semester, you probably heard me call it like the linear, or those of you who had me for Calc 1, you heard me call this like the linearization of the square root function at x equals 4. And I probably called it like L of x or something. Today I'm going to give this function a slightly different name. I'm going to call it t sub 1 of x. T, naturally, is going to stand for Taylor. 1 corresponding to the fact that this is a degree 1 polynomial. It's a linear function, as a x to the first power is the highest power of x. And what I want you all to notice about this function, t1 of x, is that it has 2 things in common with the square root function, f of x. First of all, if you plug in 4 to each of these functions, you're going to get the same output. If you were to plug in x equals 4 here, you would get 2. If you were to plug in x equals 4 into the original f of x, take square root of 4, you would also get 2. The other thing that these functions have in common are linearization here, our tangent line, in the original function, is they also have the same derivative at 4. They have the same derivative of a 4th by construction. We already showed that if you take f prime of 4, the derivative of the square root function at x equals 4, we got 1/4 as an answer. And, well, if you look at this tangent line here, if we were to differentiate this function at x equals 4, or anywhere else for that matter, you would get a derivative also equal to 1/4. So it turns out this tangent line function has the same y value at 4 and the same first derivative at 4. In fact, it's the only linear function that satisfies both of those conditions, that has the same y value and the same derivative. Any questions or comments thus far? I went through that a little bit quickly because this is sort of, so far I think this has been a review of stuff you likely saw in Calc 1, finding tangent lines. And then if we wanted to approximate the square root of 4.1, we could plug in like 4.1 for x into this and get like, square root of 4.1 is about equal to 2 plus 1/4 times 4.1 minus 4. Pretty close. All right, so now I'm going to spice things up a notch. Instead of finding a tangent line to our square root function, at x equals 4, I'm going to find a tangent parabola to our function. Our parabola, it's going to look something a little bit like this. So what does that even mean? Finding a tangent parabola. I mean, graphically, you can sort of think about it as, oh, it's a parabola that looks like it matches up very closely with the square root function at x equals 4. But what does it mean, Matt? But how could we be a little bit more formal about that than saying it looks like it matches up pretty closely? Phoebe?
Is there a reason we picked 4 or just because it's easy?
I picked 4 because it's easy. Well, easy-ish. We're going to be needing to take square root of 4 quite a bit as part of this process. And if I try to do it at a different point, like square root of 10, it would make much less nice numbers. Well, here's a key aspect of the tangent line was these two things. That the y value of our tangent line matched up with the y value of the function at 4. And the first derivative of our tangent line function had to match up with the first derivative of square root of x at x equals 4. So our tangent parabola, we're going to denote as t sub 2 of x. And there's 3 properties that we're going to want our tangent parabola to satisfy. The first 2 properties are the same as our tangent line. We're going to want that t sub 2 of 4 is equal to f prime, or not f prime, but f of 4. We're going to want that the first derivative of our tangent parabola matches up at x equals 4. And what other condition do you think we might want to have satisfied at x equals 4? Other than the y value, which is really the same as the 0th derivative of our function matches up at 4. The first derivative of our tangent parabola, we want to match up with what's going on at x equals 4 with the square root function. What's the third condition you think we might want to have satisfied? Abe?
The second derivative of 4 was also equal to the second derivative of the function.
Bingo! We not only want the 0th derivative, so the y value, and the first derivative to match up, we want the second derivative to match up as well. Because if we can find a parabola that satisfies all 3 of these conditions, the y value is the same, the first derivative is the same, and the second derivative is the same at x equals 4, then that'll give us a very nice tangent parabola which also kind of behaves this very similarly to our square root function at x equals 4. So how do we do that? Well, we know what f of 4 is. We know f of 4 is equal to 2. We already know f prime of 4 is equal to a fourth. We found that earlier. Well, I erased it now, but we found those earlier when we were looking at the tangent line. So we need to know what f double prime of 4 is. So we know what the second derivative of our tangent parabola needs to be equal to at x equals 4. So if we look at this, well, we get f of x is x to the 1/2, meaning if we do power rule, we'll get f prime of x is equal to 1/2 x to the negative 1/2. If we did the power rule a second time, get a formula for f double prime of x, Maria, what would that give us?
A negative 1/4 x to the negative 3/2.
Yeah, it is in fact going to be negative 1/4 x to the negative 3/2. Sorry, I hope you don't mind me making fun of you just a little bit here. I don't want to keep things too serious. Yeah, if we do the power rule a second time, we'll get negative 1/4 x to the negative 3/2. And please, by all means, make fun of me as much as I make fun of you. I deserve it thoroughly. So if we wanted to find f double prime of 4, we would have to get negative 1/4 times 4 to the negative 3/2, which is the same as negative 1/4 times 1/4 to the 3/2. Well, 4 to the 3/2 is going to be the same as the square root of 4 cubed. Square root of 4 is 2, 2 cubed is 8, I believe. This will give us negative 1/4 times 1/8 to give us negative 1/32. Okay, so far this has just been calc 1. Taking the second derivative, plugging in 4, simplifying to get a number is your answer. Dealing with a few, exponent rules along the way. No, I know what you meant to say is, ooh, not you. Hit it right. But we got there in the end. We need a function, in other words, a parabola, where if we plugged in f of 4, we would get 2. If we plugged in f prime of 4, we would get a fourth. If we plugged in f double prime of 4, we would get negative 1/32. So, how do we find that? Well, if you remember our tangent line that we found back in the first step had the formula 2 plus 1/4 times x minus 4. That was our tangent line approximation that told us that satisfied these, that had first 0th derivative and first derivative equal to 2 and 1/4 respectively. So it turns out that in order to have these two bullet points be satisfied, we could say quite a lot about what our tangent parabola has to look like. So in order to have t2 of 4 equal to 2, and t2 prime of 4 equal to 1/4, turns out that we're going to need that t2 of x has to be the same as this t1 of x formula. We need to have a 2 plus 1/4 x minus 4 expression. We're also going to need to have one more term, some constant times x x minus 4 squared. For some constant, I'll call it a2, which is the coefficient out in front of our x minus 4 squared term. So how do we determine what our a2 is? What constant we need to put in front of x minus 4 quantity squared to get our tangent parabola? Well, we just need to make sure that this third condition is satisfied. That when we take, or not that condition, this condition, that when we take our second derivative of this function evaluated at x equals 4, we get f double prime of 4, which was this negative 1 over 32 value. So let's do that. All right, so t2 of x is 2 plus 1/4 x minus 4 plus a2 times x minus 4 squared. Hey, James. If I differentiate this function with respect to x, what am I going to get?
You'll get 1/4 plus 2 times x minus 4. Or wait, would it be? Yeah, I'm thinking. Yeah, it's like a2 times 2 times x minus 4.
Yep, you got it. Yeah. The derivative of 2 is just 0. The derivative of 1/4 times x minus 4 is just a 4. The derivative of a2 times x minus 4 squared, we can use the chain rule on that to get just its 2a2 times x minus 4 to the first power. And then technically times the derivative of x minus 4, which is just 1. Hey, Jonah. What would we get if we differentiated a second time? Get t2 with double prime of x.
Would just be 2 times a2.
And so, derivative of 1/4 just going to be 0. Derivative of 2a2 times x minus 4, well, that's just going to be 2a2 times 1. We plus 0, technically. So here's the key aspect here. What we need in this problem is that we need t2 double prime of 4, which is just going to be 2 times a2. If we plug 4 in for x, well, 2a2 is just a constant, so plugging in 4 for x there doesn't actually do anything, or change it in any way, I should say. We need that to be equal to this negative 1 over 32 value that we got from taking f double prime of 4. And Emerson, if 2 times the constant a2 is equal to negative 1 over 32, what does that mean that a2 has to be equal to?
Negative 1 over 64.
Negative 1 over 64. So here's going to be our tangent parabola in all of its glory. It's going to satisfy the formula t2 of x is equal to 2 plus 1/4 times x minus 4 minus 1 over 64 times x minus 4 quantity squared. It's the same as our tangent line function, our tangent line approximation to square root of x. But the only difference is that we're adding in this extra x minus 4 squared term in order to make it a tangent parabola, a degree 2 polynomial, as opposed to just a tangent line, which is a degree 1 polynomial. And the negative 1/64, the reason why we have this coefficient in particular is so that we can make sure this condition is satisfied, that the second derivative of our parabola matches up with the second derivative of our square root function at the point x equals 4. Questions, comments, concerns? Alright, let's do one more of these. Let's find a tangent cubic function. Meaning we're going to find a tangent function that's like that's a degree 3 polynomial that has x squared, and x cubed terms in it. Which is going to give us something that looks a lot like this. The sort of degree 3 polynomial which matches up pretty nicely with our square root function at the point x equals 4. Well, for a tangent cubic, we're going to want 4 conditions to be satisfied. Same 3 as with our tangent parabola. We want t3 of 4 to be equal to f of 4, which is just 2. We want that if we take the first derivative, evaluated at 4, we get the same thing as f prime of 4, which we saw was a 4th. We want our second derivative to match up with f double prime of 4, which we saw down here was -1 over 32. And finally, what's our new condition that we might want to have satisfied here? The y value, we don't just want that our y value, our first derivative, and our second derivative match up. What do y'all think the new one's going to be? Jonah, any guesses?
Third derivative.
The third derivative, yes. Yeah, we're going to want that our third derivative matches up at x equals 4. Which we don't know what f triple prime of 4 is, but we'll find that in a second. So our tangent cubic function has 4 properties in common with square root of x. It has the same y value at x equals 4, the same first derivative, the same second derivative, and it's going to have the same third derivative as the square root function does at the point x equals 4. Alright, so first of all, you probably want to find what our third derivative is going to be equal to first. Let's see, this is -1/4 x to the -3/2. What would we get if we differentiated that function one more time to get f triple prime of x? Kate?
I'm sorry, can you repeat what you just said?
Sure. We know what f double prime of x is. What would it's -1/4 x to the -3/2. What's the third derivative then going to be if we differentiate one more time?
3/8 x to the -5 halves.
Yeah, I think so. If we do the power rule yet again, we'll get -1/4 times -3/2, which comes out to a positive 3/8 x to the -5/2. And if we wanted to take f triple prime then of 4, we would get 3/8 times 4 to the -5/2, which is the same as 3/8 times, what, 1 over square root of 4 raised to the 5th power? Because 5/2 is the same as taking the square root and then taking that to the 5th power. So, square root of 4, that's 2. 2 to the 5th power By the way, Phoebe, here's where it really is nice to have a nice number like 4 to work with, because otherwise if we were trying to do this at 10, say, we would be having to take square root of 10 raised to the 5th power, which would be So 2 to the 5th, alright. Do I know my powers of 2? 2, 4, 8, 16, 32, I believe. And we get 3/8 times 1 over 32, which I think is going to come out to 3 over 30 times 8 is 240, 2 times 8 is 16, 240 plus 16 is 256. It's a big number. So, where can we go from here? Well, we now know that we want to find our cubic function that at x equals 4 has a y value of 2, first derivative of a 4, second derivative of negative 1 over 32, third derivative of 3 over 256. And so then, turns out, once again, we can start off by saying that the first 3 terms of t3 of x are going to have to be the same as what we have in t2 of x, our tangent parabola. It's going to be 2 plus 1/4 x minus 4 minus 1 over 64 x minus 4 squared. And we're going to have some unknown constant times x minus 4 quantity cubed. And what we need to do is, we already know this is going to satisfy these first 3 conditions from the fact that our t2 of x satisfied the first 3 conditions. So we need to find what value must a3 be equal to in order to make this 4th condition also satisfied, so that the third derivative comes out to 3 over 256. Alrighty, so to start off with, let's take a couple derivatives. Reagan, what would we get if we differentiated all of this? Other than a scared look on our faces.
Yeah, that for sure. So you'd end up with be 1/4. No, it'd be 1/4. Minus 1/64.
1 over 64. What's the derivative of x minus 4 squared?
Just 1.
Not when we square it. What does the chain rule tell us we need to do when we take the derivative of x minus 4 quantity squared? It's a little bit of a mean question because we've been focusing so much on like integration and series lately. We haven't been doing derivatives very much.
Do you multiply it by the derivative outside, right?
Yeah. So the 2 comes down, and we'll get, I think, 2 over 64 times just x minus 4 to the first power. And then how about our last expression?
Be 3 times a sub 3 times x minus 4.
X minus 4 squared, when you subtract 1 from the power. Yeah, nice job. So there's our first derivative. We've got 2 more to go. Nora, what's going to be our T3 double prime of x then?
Negative 1/32.
Is you're just going to go ahead and simplify that? Sure.
Plus 6a sub 3 times x minus 4.
6a3 times x minus 4. Cool. Cool. And then, Mary, if we differentiated this one more time, what would we get? 6A3. Sorry, Reagan, I gave you the hardest one. Turns out to just be 6A3. So that when we take T triple prime of 4 and set it equal to F triple prime of 4, which is 3 over 256, well, that's going to give us that we need 6A3 is equal to 3 over 256. And if we divide both sides by 6 to get A3 by itself, Devin, what's that going to give us?
6.
If we divide 3 over 250, if we divide both sides by 6,
Oh.
get A3 by itself? That is correct. We're going to get a nasty fraction. Well, if we divide the top by 3 and multiply the bottom by 2, that would be dividing the whole thing by 6. 6 times 2 is 500 plus 12, 512. Turns out it's 512. And so our formula then for our tangent cubic function is going to be t sub 3 of x is 2 plus 1/4 x minus 4 minus 1 over 64 x minus 4 squared plus 1 over 512 x minus 4 cubed. Devin, you really need to work on your pronunciation. It's ooh, not ew.
Yeah.
That's even worse, but keep looking at it. What are we doing here? Carson has no idea.
Witchcraft.
Not entirely wrong. What does it look like we're building here? If we were to keep going, we get an x minus 4 to the 4th term. If we found a tangent quintic degree 5 polynomial, we'd have an x minus 4 to the 5th term, etc., etc. It sort of looks like we're going to be building up this sort of infinite sum. What sort of infinite sum does it look like we're building up? It's
A power series.
we're building a power series is really what we're doing here. And not just any power series, it's going to be a power series that converges to our square root function. A power series that I'm going to call the Taylor series to our function at x equals 4. So this is going to be our Taylor series, which is just a power series that converges to our function at a particular point at the center of the power series. At x equals 4. And it's going to have a formula of t of x. This time I'm purposely not leaving in the coefficient. By the way, I'm skipping a couple pages ahead in the packet just in the interest of time. Of 2 plus 1/4 times x minus 4 minus 1 over 64 x minus 4 squared plus 1 over 512 x minus 4 cubed plus ... Finding these coefficients is a lot of work. It'd be nice if you had some kind of nice general formula for how do you find these coefficients, like 2 and the 4th and negative 1 over 64 and 1 over 512. Turns out there is a pretty nice, pretty slick formula for what these coefficients are. Turns out that the coefficient on, say, your x minus 4 squared, your x minus 4 cubed term, or in general, the x minus 4 to the nth term, is going to be the nth derivative of f evaluated at 4. So if n was 3, we'd be taking like f triple prime of 4, for instance, divided by n factorial. So if we were to take the nth derivative of f evaluated at 4, in this case that would be 3 over 256, and we wanted to multiply by 1 over 3 factorial, well, 1 over 3 factorial is 1 over 3 times 2 times 1 is 1/6. That would actually give us the 1 over 512. And if we took our negative 1 over 32 and we multiplied by 1 over 2 factorial, 2 factorial is 2 times 1 is 2, that would just give us the minus 1 over 64 term. That's our coefficient on our x minus 4 squared term. And so kind of using this general expression, what this is going to give us is this is going to be a power series that converges to f of x equals square root of x at x equals 4. Or centered at, I should say, got the word centered, at x equals 4. And here's the cool thing. As long as the function is what we call infinitely differentiable at your point, meaning you could just keep taking derivatives forever, if you give me any function like that, you can keep taking derivatives forever, this method is going to produce a power series that converges to your function. It's going to give us the Taylor series. And if you were to ask a computer, like Dr. Webster, I think he's a computer. Seriously, if you like look inside his head, it's all like gears and oil and circuits and such. This is how he would compute a function like square root of 4.1. So he would take a Taylor series, plug in 4.1 for x, and use that to much more quickly approximate square root of 4.1 than he would trying to do square root of 4.1 directly, which is a big pile of F. Alright, hope that gives you a sense of what standard 16 and 17 were going to be about, is this idea of given a function, find a power series converging to that function using this idea of tangent lines, parabolas, cubics, etc. We come back on Monday. We are going to have our last midterm. And so today was the last day of new content for the class. It's just exams from here on out. Hope you all have a good weekend. Hope you all have a chance to relax just a little bit. Seriously, try and get some sleep. It'll do you a world of good, I promise you. Even if you don't believe me. Devin doesn't believe me. I'll see you all on Monday. Have a good one.
Thank you for your